Hello everyone. Today we're going to talk about applications related to computer vision, especially for mass-produced products such as industrial components or food items. I'll start with the fundamental use cases, then move on to the required hardware and production line conditions. We'll also cover specialized scenarios, such as 3D vision systems, and provide a comprehensive overview of how everything fits together. Let's start by looking at the real needs behind these applications. Think about the current situation. Taiwan's external environment is getting tougher. Labor costs keep rising, and on top of that, US tariffs are putting even more pressure on manufacturers. Recently, we spoke with a factory that had to hire a dedicated employee whose only job was to watch the production line for packaging defects, 8 hours a day, every day. We pointed out to them that hiring just one person for this role costs around 40,000 new Taiwan dollars per month, including labor and health insurance. That's almost 500,000 new Taiwan dollars a year, and roughly 1 million new Taiwan dollars over 2 years. With that budget, they could easily build a full computer vision inspection system to detect these defects automatically. A vision AI system doesn't get tired. It doesn't get eye strain. It doesn't ask for sick leave. And in just 1 to 2 years, it practically pays for itself. So the real question is, why wouldn't you invest in this? The core principle of computer vision is to analyze color, intensity, contours, and even text and symbols to perform deeper pattern interpretation. In typical use cases, this includes tasks like checking whether labels are misaligned or missing, verifying whether multicolor wires are arranged in the correct sequence before crimping, and more. If done manually, these tasks are not only inconvenient but also highly error-prone. In the food industry, for example, vacuum packaging can easily create cracks or surface damage, and products may also be compromised due to human handling errors before packaging. Computer vision helps detect all of these issues with far greater accuracy and consistency than human inspection. Once you've determined which product defects and characteristics need to be analyzed, the next step for the manufacturer is to plan how to install the camera system and the necessary auxiliary lighting on the production line. Computer vision systems differ greatly from standard surveillance cameras. Because they must capture images at very close distances and magnify tiny defects, traditional security cameras are not suitable. Most security cameras are designed to focus at distances of 4 meters or more, while inspection systems typically operate at distances between 5 centimeters and 100 centimeters. This is why we use industrial cameras equipped with specialized lenses. These lenses are designed for close-range imaging and provide much stronger image clarity and contrast. As a result, a single industrial lens often costs over 20,000 new Taiwan dollars. Lighting is another critical factor. Although white light is commonly used for illumination and contrast enhancement, certain applications require red light or other wavelength-specific lighting to highlight particular product features. Proper lighting quality is extremely important. If the illumination is uneven or poorly aligned, it can easily lead to misjudgment in the vision system. Next, let's talk about more advanced and specialized computer vision methods. In some scenarios, when the system needs to measure depth in addition to surface features, 3D vision technology becomes necessary. For example, certain automotive and sheet metal manufacturers often face issues where slight scratches appear during production. In these cases, a 3D inspection system is required to determine whether such defects exist. High-sensitivity 3D vision technologies can detect even micron-level scratches, making them extremely powerful. However, because these systems are relatively expensive, manufacturers should consult experts beforehand to determine whether such a high level of precision is truly required. Otherwise, companies may end up over-engineering the solution, using an expensive tool for a simple problem or, on the other hand, choosing a technology that is not accurate enough, leading to miscommunication, mismatched expectations, and even disputes between vendors and clients. The final stage of computer vision inspection is, of course, removing the defective products from the production line. At this point, The vision system provider must work closely with the automation equipment team or the PLC integrator to determine exactly how the defective items will be rejected. Depending on the production setup, this may involve blowing the defective product off the line with an air jet, using a mechanical diverter to guide faulty items onto a separate track, or, in some cases, stopping the production line so that workers can manually remove the defect. This coordination between vision engineers and automation/PLC engineers is crucial to ensure that the rejection method aligns with the speed, safety, and operational requirements of the production line. Finally, we need to take all the computer vision results and perform mid to long-term analysis. We once worked with a dyeing and finishing factory where the chairman wanted to build a full AI digital twin system for the entire plant. We advised him that the first step should be implementing computer vision to detect color deviations in dyed fabrics. By comparing the detected color differences with various PLC production parameters, the factory could gradually build a predictive model for producing high-quality dyed fabrics. Over time, this system would not only reduce color variation but also significantly lower related production costs.